more than a lot of them, because it's practical and it's something that you will find yourself doing quite a bit, especially after this discussion. So I say consider the semi-linear model. And so if I took away the FJs, this would just be your linear model that you're used to seeing. So I could take functions of those FJs. It could be a linear combination of a beta and those. So I'm making a linear combination of those. What I have in mind for the FJs are maybe polynomials, something like that. So it could be a polynomial function of x's. And in the data sets that I simulated, I have made those polynomials in some of them. So I've given you 3 data sets to play around with, and I know how I constructed data. And so, just as a helping hint, I didn't go past cubic polynomials. Okay? So, because that can blow out the dimensionality on this problem quite a bit. And so, if there's p covariance in here, then polynomial evaluations could expand into a whole bunch of extra betas for each polynomial term. And so that would be a much harder problem. So no bigger than cubic terms in here. But basically we want to figure out which of these betas are zeros, which they're not. So i.e. which terms show up in the model. If a beta j is 0, then it wipes out that whole term right here. Probably more realistically, I would probably have to write in a different beta for each one of the polynomial terms. And so I wanted to write this quite generally. So I'd probably need a vector of betas right there that I could write down. But you get the idea. And so also in this model, when I generated data, I used normal air. Okay, so no mixtures. I could have made this problem harder by building in mixtures, and you have MCMC facilities also for working in mixtures. So if I combine MCMC procedures, they still all converge to the right thing. So if detailed balance holds in each little chunk of your MCMC Gibbs sampler code, then detailed balance holds in the whole code. And so you can build in the mixture stuff on the air components. You can do all kinds of things. But this problem is exclusive to looking for betas that are 0. And so I want you to work out the Bayes factor for comparing 2 different models. We'll talk about that briefly in just a moment, but I'll show you what you need to work out. So I have 2 different models with 2 different sets of betas that are active, non-zeros. And I want to be able to compare them. So I want you to write down the Bayes factor for that. Dan made an important point that Bayes factors for evaluating models can take care of any type of model you want to compare. Nested, non-nested, same error structure, totally different model. Bayes factors. So, beautiful thing.
With regards to that model, the beta j, does that apply to all polynomial terms of given xi?
That's what I was saying.
Okay,
you would want a different beta for each
Gotcha.
polynomial.
I wasn't sure if you're saying you want to do it that way or
you can't write this down generally for any class of f's, without saying, well, I mean this specifically. So I was trying to generally capture something right there, but you'd have a different beta for each polynomial term.
But
probably
in
in
some
general.
way, there's two beta and beta for.
That's the way I read it.
Okay.
Let's see. Try to get this thing back up.
I think it's from the Google.
Yeah, obviously. Wiggle.
You want to try a different computer?
Well, it worked a second ago, so I'm kind of going on the theory it's going to work, and I just won't move the computer yet.
One question.
Yes,
Is this homework going to be due Wednesday?
it's going to be due on the final exam.
Oh.
So, at that day. So, if you'd like, I could probably make it due the day after finals or something like that, because we have all finals weeks. So, maybe I'll make it due on Tuesday or the Wednesday. How about that?
But then we don't know whether we didn't. Students.
But yeah, you could come and ask me maybe which model did I use. Maybe I'll post the correct model on whatever day. But I think going through this, you should be able to tell. So how can you tell if you've done it right? Can anybody answer that question?
Model converge, maybe.
Okay, so if your algorithm converges, and so it converges to something, so that's a guaranteed 100%, this is correct, right? No.
You can set variance to 0 and it will always converge.
Okay, well, hey, great, yeah, exactly. So depends on the model. Also depends on how your errors cancel each other in your code. Maybe it converges to something, but maybe it's not right. So how would you check all of this stuff to see if you're satisfied you've done this right? This is the job in practice. Somebody walks in with a data set, and if you say you ran lasso or you did stochastic search variable selection, which is hopefully what this lecture is about today.
Send the data by ourselves.
Yeah, thank you. So I've said this before. Simulate out of these functional forms. You know, I've told you which forms I'm using, no bigger than cubic terms. And you can set up true model and see if you've discovered true model appropriately. So how often are you discovering true models? So if I were gonna do something on data that somebody handed to me, I'd always build the simulator, every single time. So it's kind of brute force. It's kind of crude, I guess, but it does also work. Okay, getting frustrated.
How was it?
What's that?
How was it working like 2 seconds ago?
I don't know. If I knew the answer to that.
Yeah.
I'm going to try this one more time, and then I'm going to give up. So, okay. So, what I want you to do in problem 1, so this is the only math you really need to do, is work out these base factors for comparing these models. Okay, I'll write down the equation that you need to solve on the board. But basically, you need to work out 2 integrals, and there's a lot of cancellation between the denominator and everything else. So the numerator and the denominator, lots cancels out if everything is nested. And so you get clean forms out of this that you can efficiently code up. But I don't want to work that out for you. I want you to just do this one last homework assignment. And then I want you to download a data set. So these are all going to be on the web page. So there's 3 different data sets. The first column is going to be the y variable. And the rest of the, I think I put in 50 extra columns, are going to be x's. Okay? And so, yeah, I've given you 50 data points too, and 50 covariants, just to make the point that you need to do model selection. And so a lot of problems do come at you this way. It's you don't know what to model. And nowadays that we can get our hands on lots of data, this is every problem probably. And so a little bit of difficulty in here, and there's 3 different data sets. Going back to the homework, I've done 3 different things. So the first data set is relatively easy, and I didn't do anything too crazy. I will point out that the key to that data set is to build in an intercept. If you did not do this, if you didn't think, of course, why would I not build an intercept? I didn't put it in there. But if you don't, you will not identify the right model, no matter what you do. And so intercepts are wildly important in models, and I don't like models without intercepts. If you're like, the power of my calculation is just too low, and I can't estimate the intercept with how little data I have, I've got a problem with that. Don't think you have enough data. I like intercepts, even if you don't think everything is linear everywhere in the space. You know, if you misspecify a data point in a model, it has an ability to steer your whole regression line. An intercept and anchoring it down somewhere, maybe arbitrary, has an even bigger influence. It steers your whole line. It will go through that point. And so build in an intercept, and problem 1 is going to be easy for you. Probably a lot of these methods will agree. I want you to look at lasso BIC, AIC, and this algorithm that I'm going to talk about today, SSVS, Stochastic Search Variable Selection. So SSVS, Stochastic Search Variable Selection. And that's just the thing where you're running MCMC and you're using these point mass priors. So beta J is equal to 0 plus some amount of alternative mass on it being something different. Given whatever your hyperparameters are. Now, we've talked about this alternative prior as mattering a ton, and it does. You can experiment around with it, but let's just start easy and use the conjugate form. If I didn't give you the conjugate form, you wouldn't work out the Bayes factor analytically. And still, most people do this. So keep in mind, there is an imbalance in rates when you use this sort of prior. I will say most of the people using SSVS are using that form of a prior. This thing matters a lot. And so you're going to have to decide how you tune it. Now I've given you some prescriptions for a problem like this. In variable selection, I want to talk about if each of those columns are important. And so that's kind of a loaded question. What do I mean by importance? And so should I standardize, should I not standardize? If you don't tell me anything about the variables and it's just data, I'd probably say that standardize it. Saying that the way I generated it is pretty standard. It's not too crazy. And so I didn't put in all these anomalies or anything like that. And so if you standardize it, you've probably got some good choices for psi right there. But for the same reasons as hypothesis testing, that's a sensitive parameter. Saying that, in Lasso, everything's sensitive to that. So you're going to have to talk about how you tune that. And BIC and AIC, they're methods for comparing two models. So there's no tunables there. But you're going to need an algorithm for searching through that space, for comparing all the models. How many models do you need to compare here? 2 to the p at the minimum. If I didn't take a polynomial functional evaluation of the data, but it could be 2 to the 3p, which is a pretty big number. So intercepts in, so the model, so we don't have to discuss that and say plus an extra evaluation. Intercepts are in my models, and they will make a difference. So I want you to compare the data set using these 3 methods. So you will have to develop algorithm for searching through this. Say Matt, when I used it, if somebody would have given me this problem 15 years ago when I was in graduate school, I would have thought this was just an epic problem. You know, wow, so little data to discuss, you know, when entertaining so many possible models. And so 2 to the possible 3p, that's a lot of models. And so they used to give us stuff with like 10 covariates and make us decide. But we've got computers now, and we can do this stuff. So while there's a lot of models to search through, you still probably don't want to compute every one. That would take a long time, but you probably could. You probably don't need good algorithm, you know, if you're just going to compare everyone and get the whole distribution of Bayes factors, you know, and then discuss which models you like the most. I'm going to show you algorithms for searching through these spaces. And the algorithms that we develop here for searching through models using that prior can probably be transferred over for searching through BIC or AIC. So they're just search space algorithms, comparing a whole bunch of stuff. Which ones do you want to dwell on? Which ones do you want to compute over? High probability models. Those are the ones you want to explore. So MCMC is kind of cool because it will spend most of the time looking at the high probability stuff. That's what MCMC does, and that's why it works well in high dimensional spaces. There's a ton of software for this stuff. So R has 1 million facilities for this with graphs. MATLAB has a whole bunch of stuff. I was pretty impressed. I was playing around with it last night. And wow, this is incredible. All this software with graphics, and we used to have to build all this stuff. And nowadays it's out there for you. So if you want to use that software, that's fine, but coding this up shouldn't be that difficult. And so I want you to code up at least one of these things in here. And so tell me which one you coded up. If you want to code them all up, that's what I would encourage you to do. If you code them all up, and you know all the literature for searching through these things, and you can make good decisions depending on the models and data people bring you, you can be a professor. And so the more you know about this stuff, you'll be better off. So, I did do a search on stochastic search variable selection, and I came up with a laundry list of papers. So there's a ton of papers written on this, stochastic search variable selection, all of these papers. And so you'll see one name that pops up a lot, George and McCulloch. So they kind of wrote the original paper on this, the highly cited paper, and I'll show you that in a second. But if you do this in Google Scholar and you click on that, you're going to get a book. They actually developed this into a book, I think, in '95. And so this stuff is in books now. It's been in books for a while, so presumably it's kind of old. And so there is a lot of development on the algorithms for searching through these models efficiently. And I'm going to show you one such algorithm, and it's not going to be the most efficient algorithm. And there's going to be a major downside to this algorithm too. But there's a lot of different adaptations to how you fit the SSVS model. So lots of papers you can read through. I didn't see the seminal paper by George and McCulloch in '93 in this list. So that's how I typed it in. I'm sure I could be more specific and narrow down my search. But I did go to just plain Jane Google and search on everything. And I found this paper right here on the 4th hit. And this is in JSTOR. So kudos to JSTOR, you're still relevant. You can find the original Jazza paper here. So if you're on campus, you'll be able to download this. And so you can look through their citations, but you can look through other people's citations as well. And that's how you get a handle on looking through the literature. But there isn't one implementation of this algo that searches through models using this product. Okay, so there's model that I've told you about, and then there's algo to actually be able to sample from that model. So you can read through this paper if you'd like. There's a whole bunch of other papers. This is one of my favorite versions of this algorithm. And realistically, it's the exact same thing that was written down 5 years earlier, this by Coe and Mollick. It's also in JSTOR. And they have a different representation for this particular model. So instead of betas, it's this continuous thing that's modeled by a point mass mixture. They talk about beta times gamma, where gamma is an indicator function. And they put a model on that, a Bernoulli distribution. And it turns out to have the exact same model formulation that we're writing down here. However, what are the priors in the Bernoulli? This is P in the Bernoulli that you sample. And so it has the exact same mathematical representation, but algorithmically it's different. And you can get a lot of efficiency by coming up with new algorithm or mathematical representations of your model. And that's what they did in Coe and Mollick. And later on, I showed how to use this sort of Coe and Mollick framework using one of my previous samplers, the multi-set sampler, that also shows up in Jazza, and that can be found in JSTOR. This showed up just last year. So I had done something where I have this neat MCMC algorithm, and I showed how to adapt SSVS to Coe and Mollick's framework. That's what I do for a living. And that's why I get paid. And so basically, you take other people's stuff and you generalize it again, and you show a computational advantage in something. So that's kind of the universe I do research in. Okay, so homework, you'll look over this data set, compare these 4 techniques. Basically, all you're going to be saying is which model did you select, and also tell me the coefficients that go with that model. So don't just tell me variable 17 is in the model. Tell me what the coefficient for variable 17 is. Eventually, I'll tell you what my true model is. If you run your own simulator, you won't care. You'll be like, I think I did it right. I think I got it. Feel pretty confident. Okay. Problem 3 and 4, similar. I want you to do it on more advanced data sets. So I did something to this model, and I made it more and more complicated at each step. So you might want to check for multi-collinearity. You might want to check for polynomial terms, things like that. And so, yeah, I did throw collinear stuff in there. Let's just keep in mind, if I did build in collinear stuff, that solution that we're always pointing to doesn't exist. It's not the MLE. And if this were a flat prior, right here, if I ended up using a flat prior and I tried to estimate the posterior mean or mode or map, they're all the same under a flat prior because of symmetry, the expectation wouldn't exist because that's the posterior expectation. However, if I use a proper prior, not a flat prior, I'm automatically doing ridge regression. So that's auto ridge. So using proper conjugate prior is ridge. And so I like to build in a little bit of penalty so that I can get around the multi-collinearity problem. So if I didn't check multi-collinearity, at least I'd be going for a solution that existed. But there would be a phenomena that would happen in my MCMC. Let's imagine I had two columns that were collinear. So what I mean by that is I take this column, I multiply it by some number, and I form another column. Okay? So they explain exactly the same data. If I standardized everything, it would all be the same stuff, same columns in there. If I forgot to check that, that solution wouldn't exist, and a lot of solutions wouldn't exist. But in MCMC, if we're going to be iterating through and sampling through model space, I'd end up seeing models with this column in it sometimes, and then this other thing would come in. And these things would be negatively correlated with each other. They'd switch in and out. They would have equal predictability. I'd be getting some solution, but you'd want to be able to detect that in your sampler. What I usually recommend to people is study the math, understand what you're doing first, and do the simple stuff that we're supposed to do as statisticians. Algorithms won't solve every problem for you. Sometimes you have to make some judgments and do some pre-processing. So check for collinearity in the variables. If you see collinear stuff, just rip it out, because it's going to make your algorithm take a long time to converge. And you won't be able to make sense of the variables. So if you had something like column 17 and column 2 being collinear, and they were going in and out of the models, your posterior probability of column 17 being in the model would go down by half. And all of a sudden I'd have half of that probability also on column 2 coming in and out, and they'd be swapping. And so I'd misidentify the importance of that variable. So that would be a mistake. So still do all that exploratory stuff. Ben?
One question, is there a better way to identify this collinearity than pairwise regression?
And just check. Yeah, I mean, I would just check the correlation. That's really all I do. And so if you want to build another algorithm over the top of your MCMC, I used to think about doing those sort of things. I was like, I could, or I could just do the basic exploratory stuff. So I don't think it's too much of a burden to check correlations. So I don't have any better way to do it. But you might have two variables that are created in a linear combination that make up another variable. You would see those in the pairwise correlations. You would detect them and see that they're all pairwise correlated with each other. So I think it's a reasonable thing to do. What do I normally do when I do that? So we've got 50 variables, right? So now I need to make a 50 by 50 matrix or something like that and I don't look at that stuff. I just run in a loop and I put a threshold and I say, show me stuff that is collinear above like 0.5 correlation. And then I move in and I say, show me stuff that's over 0.6 correlated, 0.7 correlated. And then I make a judgment about those things and I look at what those variables are. I still think you should do all that stuff. So modeling and computation is cool, but still do the basic stuff. It'll help you in my problem. Okay, lots of papers. Let's talk about the specifics. start easy before we get into the algorithm. Compare two models. Okay, so let's just make this real easy. P is equal to 3. This is the dimension of the problem. Okay, so my models, model 1, I'm just going to write down is 1, 0, 1. In model 2, I'm going to denote as 0, 0, 1. Those are arbitrary. So what I mean by this is yi is equal to beta 1 xi1 plus 0 plus beta 3 xi3 plus error. This is what I think the model is when I denote it by these indicators.
Should we add the intercept whenever we begin from here?
Yeah, maybe so. So I haven't said what that is. So mathematically, I get to be general and say, oh, all of my first column, these x's are 1s. And so it still fits the notation.
Okay.
So, but yeah, I would probably usually have my first column in my X matrix being 1s.
So can you have like beta 0 times something and then just...
You could write it down that way, and if you're going to write it out using linear algebra, which I'd encourage you to do in this problem, you'd have a column of 1s. And your beta 0 would refer to that. Yes, absolutely. So this is yi is xi3 beta 3 plus error. So that's what we need. So how do I compare these two models? It's not a trick question anymore. Bayes class, how would we do this as Bayesians?
Find the base.
Bayes factor. So Bayes factor calculation. So what I have to do is I need to integrate over my likelihood, and I'm going to write it out like this. Beta given model 1 and all of my data. So I can write this fairly generally. And then I'm going to end up having a prior over model 1 on my beta. So I'll be more clear about that in a second. And my betas are coming from model 1. Integrate. I'm going to use the same likelihood representation because I'm just using indicators in my betas to express everything. And so, model 2, X, proper prior, under model 2. So what's this prior right here? What am I using? Got these two parameters coming in. So how am I writing this down? The likelihood's easy, same likelihood we always write down. Let's control everything through the priors. So I could turn off the betas in the likelihood, but I don't need to. I can turn them off in the prior. I'd have the exact same influence. So I'm not even going to muck around with my likelihood representation. That's e to the minus 1/2 divided by sigma squared, y minus x beta transpose y minus x beta.
So should it be like delta for that is equal to 1 and 0 and 1?
Yeah, so what's my prior here? How do I just write it down? Let's remember, this is what we've got. Beta j is equal to pi naught delta beta j is equal to 0 plus 1 minus pi naught. And I'll write down normal over beta j. What's my mean? That's 0. So that's just where I'm centering this thing. So, and then I've got this parameter. So what am I writing down right here in the integral, in the integram? What goes there? Same process every single time. That's what's beautiful. If you get this right, it's that answer every single time. So what do I throw down right there? What have I got? Killing me. Yeah, so which betas? All of them? Just the ones in the model, right? With which prior? Rob, just this thing, right? So it's just that. So this is just going to be absolutely, thank you, Melissa. So you got it. It's just going to be this thing. Root 2 pi. I've got psi right there. E to the minus 1/2 beta j minus 0 squared over psi squared. And I've got 2 of these. So I'm going to do this for this parameter that's in the model, 1 times, let's be really clear about this, 2 pi psi e to the minus 1/2 beta 3 minus 0 squared over psi squared. That's it. That's what goes in there. So what goes right here? Now we're getting real easy. It's pretty repetitive.
So you just use one of those terms?
Just use one of them. Yeah, absolutely. Psi. I don't have the other things in there. I've determined that there are zeros. So no way to smear mass over that space. And this was beta 3. Beta 3 squared over psi squared. And so you'll notice that this has more penalty on this model right here because it's bigger. So not all of these root 2 pi's are canceling. Not all of the psi's are canceling. We don't have full cancellation in there. So remember, we don't have cancellation in our base factors usually. Only the terms that are the same in the models will cancel each other. So this has more penalty because it's a bigger model. So I'm just going to write that down. More penalty. Than this. Because it's bigger. Automatic penalty. So automatic regularization. At least there's some mechanism. The Bayesians at least thought about the right thing, and they would argue asymptotically. They're going to do the right thing so long as this thing right here isn't infinity. Eventually, but we want to do it well with even smaller data sets. So that's the base factor you need to work out for comparing these two models. Let's say I want to do this stochastically. And I wanted to think about a probability of this model being correct. So simple question, we've answered this a lot of times. What's the probability of model 1 given the data? Bayesians get to answer these questions. We put a random measure over the model itself. Easy. Yeah, that thing. 1 plus 1 minus pi naught phase factor that we just computed. And so I'm going to write this down as model 2 compared to model, or I'll write down model 1 compared to model 2. Just to be clear about this, inverse, inverted. So this is going to be the probability of model 1 given all of my data. And I probably should have written y's in here as well. This is regression that we're talking about. So I've got y's and x's. It's going to be this thing. Real quickly, what's the probability of model 2 given our data? 1 minus. So we can do those sort of comparisons because we're living in a probability space. So we're governed by the rules. If you do that sort of thing with p-values, it doesn't make any sense. They're not additive. They're not random measures on the thing that you're testing. They're random measures about more extraneous data. So that's what it is, p-value. So it's a statement about more extreme data given a hypothesis. So I could do the 1 minus thing. I could write it down a little bit differently. I could write it like this. So 1 minus pi naught over pi naught, Bayes factor, M1 given M2, and I'm going to invert this whole thing. So this is inverted, the regular term, and I'm just going to flip that around. And I'll invert this. You'll notice that I just flipped over the Bayes factor and the hypothesis. I changed the roles of which hypotheses I was comparing. But I really just flipped this thing around and changed how I was talking about that. And so to go the other direction is just flipping over the Bayes factor. A lot of times I pick this to be commensurate to how big the models are. So also, you might do that, or I might just say half-half. And so, and in our problem, it probably doesn't make that much of a difference. I can build in more model penalty if I want to here, and talk about how many parameters there are. So I can change my metrics if I want even sparser models. And you'll see people do this. And effectively, what they're really going to change is this thing too. So all that horseshoe stuff that we read about nowadays that people say don't do lots of do horseshoe. So Ryan, you've heard that, right? No, not yet. So keep listening. This will come up. I bet you compare it one of these days. And they're just talking about a different prior right here. So, but basically all the Bayesian model selection schemes are talking about how you pick pi naught and how you pick alternative prior. That's it. So penalize things differently, and in some problems you'll be better than somebody else. I guarantee you can write a whole paper about it. So hopefully it's useful and generalizable. Okay, so all we need to do now is build a Markov chain that takes into account these probabilities and be able to search through our search space. And that's what all these different papers that I just showed you differ in. How they talk about searching through the whole space. So I'll show you one such algorithm. I'm just going to make this up right now. So MCMC for searching through probabilities of models. So model I'll write down is these J models right here, given all of our data. So this has a name. It's also known as SSVS. Your MCMC schemes for searching through this, they're all SSVS, so long as you're using that point mass mixture prior. Okay, there's differences between how you implement these things. So I can do the 0th step of my sampler. 0. Initialize. And I'm going to write it down like this, model. And I'm going to write down 0. I'm going to give myself 2 indices to be a little bit redundant in all of this. So I'm going to give you an indice for each iteration through the loop. And I'm going to give you an index for each variable. And we're going to update them all separately. So this is going to be MCMC iteration. And this is going to be our variable that we index. Variable that we update. Okay, so maybe I say that I know what p is. In your problem, you get to know p. This really doesn't change if you do or do not know p. P is going to be the limit of your data set. Okay. So update this. This is going to go J. I'll let this be T goes from 1 to cap T. I'll let this be j goes from 1 to t. Okay, so my scheme is going to update each variable at a time. And so for me to take a whole sweep through the model to possibly change every variable, I have to march through p times. Might not like that. You might say, hey, I want to update a lot of things at once. There's prices to be paid for that. Most schemes do update the variable one at a time. So here's my algorithm. For t goes from 1 to cap t. For j goes from 1 to t. And all I'm going to do inside this loop is keep flipping coins with these probabilities that I can compute. And so I'm going to have a model t. So up here I have my first model. Right here, I'm going to compute the Bayes factor. So compute Bayes factor for updating beta j. So that's all we're going to do. And one easy way to conceptualize this, if it's a 0, talk about the probability of converting it into a 1. And if it's a 1, what's the probability of turning it into a 0? So I'll write it out like that. So if beta j is equal to a 1, what I'm going to do is I'm going to compute this Bayes factor. Bayes factor is going to be the integral likelihood. Well, I'll just write Bayes factor, and I'll just say comparing beta j equal to 0, given everything else is the same. Model Tj is the same. So all the other betas, whatever they were, I'm going to keep them all the same. If beta j was 1, or sorry, if I should write model Tj. This is beta j is not equal to a 0. That's what I mean to say. Then I compare this to the model. Everything else is the same except the betas, the beta j's. I'll say mtj. So I'm going to compute this Bayes factor. Put this a little lower.
What does it mean that everything else in MTJ is the same except for MTJ?
So I'm going to look at these vectors right here. So I'm going to have some model. Let's say this was my model. And let's say this was j. So if this was a 1, let's just write that as 1. That's the way I wrote it down. Then I'm going to compare it to this model. 1, 0, 0, 1, 1, 1. So these are the same.
So it's a local search algorithm.
That's right. And these are the same. So I'm only going to compare that one interchange. Okay? You would need to write a little bit in your if statement to check all of that. But I think we get the idea. Else, if this thing was a 0, then I'm going to compare it to the model. So I'm going to say compute the Bayes factor for comparing beta j not equal to 0 to beta j equal to 0. So I'm going to get my Bayes factors out of this. So I've got the appropriate Bayes factor for comparing these two models. One is the inverse of the other. So just to let you know. So if you're going to switch it into a 0 or switch it into a 1, these Bayes factors are just inverses of each other. And then I'm going to compute the probability of switching your model. This is 1 plus whatever this prior is. This will be the probability of old model to the probability of new. You haven't come up with notation for that, but that's just your prior odds. Possibly that's just a half and a half and it cancels out. Bayes factor inverse. Invert. So if I switch, then I update that one variable. So if switch. So what I'm going to do is I'm going to check my probability. Right here, I'll just call this PR. Probability is less than a uniform. So I'm going to just sample a 1 or a 0 with this probability. Then I'm going to end up letting MTJ, and I'll say it's going to be (1 minus 0). Does this work? MTJ, absolute value. So I'm just going to update that thing. So what did I just do? I just made this up right now. If this was a 1 right here, it changes it into a 0. If this was a 0, it changes it into a 1. So else, don't do anything. And that's it. So here's my rough algorithm. I just made this up right now for flipping coins. I can make up other algorithms where I can try to switch 2 things at a time, or 3 things at a time. Decide which groups I want to switch at a time. So many different variants of this. But that's stochastic search variable selection. If I wanted to know the betas as well, after I have an MTJ that's a 1, update its beta from its full conditional distribution. You can work out a full conditional for a regression model. It's pretty easy. Saying that, this isn't the only such algorithm out there. There's a lot of them. Somebody tell me just real quick before we convene, what's the hardest part of this algorithm?
So I think the assumption of this algorithm is that beta can only be 1 or 0.
MJs. So MTJs.
Yeah.
Betas can be anything.
Yeah, so MTJ can only be 1 or 0. What about, so it's possible that, also you mean whether we take this beta J or not?
So there, I don't think that there's any disadvantage by saying that only the MTJs can be a 0 or 1. It's just indicating what's in it or out. There's no middle ground. You're either in or you're out of the model. And so the hardest part of this algorithm is computing Bayes factors and being able to load them all up. Let's imagine I had models where I couldn't do the integration up front. That's oftentimes a hard problem. And so can you integrate all the betas out of your regression model? In the linear case, you can. And so if you can't work out the Bayes factors, you're hosed on this approach that I just gave you. And so what would you do to remedy that? I want you to think about that over the weekend. I can think of an infinite number of solutions right now. I'm not kidding. A lot of them have a lot to do with each other, though. And so there's a lot of ways I can tune it. But there's an infinite number of ways you can solve that. And there's almost an infinite number of papers out there on that problem. So,
Can you use maximum accuracy instead of Bayes factor?
well, you won't be solving the same problem. So I would say that you cheated because you solved a different problem. So, and maybe that's an approximate solution. But how would you end up revising your MCMC is what I'm really asking if you couldn't work out the Bayes factor. So you couldn't do the give sampling explicitly. I want to just point out, by just flipping these coins, just point and flip at every step. Change a 1 to a 0 or a 0 to a 1. Maybe. Just working out the probabilities. The hardest part of all this is just working out that integration up front. But this is just Gibbs sampling. So I'm just Gibbs. And so Gibbs is a pretty neat toolbox for starting out. Then
Maybe some accept rejection based on the.
it's not accept reject because my rejection steps get held. I don't throw it away. So it's fixed in the same place. MCMC and accept reject are not the same.
Well, I mean, I was.
Move or stay.
As a resident.
You could. Oh, yeah, okay, fair enough. Yeah, let's come back and talk about all the infinite solutions. But yeah, you could. Thanks, Shane.